Alright guys, welcome to today's class. Today we're going to continue where we left off at our previous lesson and do our homework and our lesson today. Alright, let's get started. Example 19. A positive integer is said to be a quadruple factorable if it is the product of four consecutive integers. How many positive integers less than 10,000 are quadruple factorable? Well, the key thing to notice here is that we want the four consecutive integers to be less than 10,000. So this means that it should be around 10. Since 10 to the fourth is like 10 to the fourth is actually 10,000. So if we take 9 times 10 times 11 times 12, this gives you 11,800. All right. But what else can we do from here? Well, notice that if we take one step down, this becomes 8 times 9 times 10 times 11, which is indeed less than 10,000. So 11 is the greatest number to be in this set. We consider the greatest numbers in each of these quadruple. Then we have 1 times 2 times 3 and 4, which is the least. This is equal to 24. So 4 is the least greatest number. So it'll be 11 minus 4 plus 1, or 8 as our answer. There's 8 possible positive integers, quadruple factorial. Right? Now let's move on to example 20. How many even positive integral factors does 6 times 6 have? We know what 1001. This is just 6 times 1001. Alright? This is just 3 times 2 times 7 times 11 times 13. Alright? So sometimes 11 times 13 is 1001, and this one is 6. This has a total of 1, 2, 3, 4. There's going to be a total of 4 2's. Okay? If I'm correct. That's 2 times 7 times 11 times 13. We want even, so we don't consider the 2. So we only consider 3, 7, 11, and 13. How many factors does each of these have? Well, this could be 3 or 1, 7 or 1, or 11 or 1, or 13 or 1. That's a 2 to the 4th power, or 16 possible ways. Since 2 is guaranteed to be there. So the answer to this question is just E. Alright? Now let's move on to problem 16. If 2 to the n is a factor of 20 factorial, what is the largest possible value of n? Well, notice that 20 factorial can be written as 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. As you can see, we want to find the largest n. That's just that 2 to the n is factor 20 factorial. So what we have to do is just find how many 2's are in there. For example, 2 has 1 factor of 2, 4 has 2 factors of 2, and so on. Well, if we do that for every single even integer, add all the 2's up, number of 2's up, we should get the answer of C or 18. You can check, double check, and this is indeed right. Alright, now let's move on to problem 17. The number 596,505 can be expressed as a product of n times p. Now, this question is a bit tough because we want to find n plus p, but these are 2-digit numbers, which tells you this is a bit of a hard question because we don't know what n times p is. Don't really. In other words, it's just going to be a factoring marathon, basically. Like, since we don't know what the factors are, we're going to have to guess and check on every single prime number. Alright, so notice that this is odd. So this is definitely 2 doesn't work. We can check it out and then get 3 times 5 times 7. All of 3, 5, and 7 both divide into 596,505. Continuing down the line, we can get 13 also as a factor, and 19 as a factor, and 23. This is the factor. Now the second part is the next hardest part. So this factoring was the first hardest part. Second is to find the combining, since there's a total of 6 factors, and we want to make it into 3, we have to combine 2 of these numbers into 1, such that they're 2 digits each. Well, notice that if we combine 7 and 13, 5 and 19, and 3 and 23, we get our 3 2-digit numbers. Or 69, not plus 95, and 91. Adding this all up gives you a grand total of 255. So the answer to this question is A. Alright. Now let's move on to problem 18. How many odd perfect square factors is 2 to the 4th, 3 times 3 to the 6, times 5 to the 10th, times 7 to the 9th? Pretty sure we talked about this question in the last class. The important part here is just notice that we want odd, so we don't include a 2 for 4th. We get 3 to the 6th, 5 to the 10th, and 7 to the 9th. Alright? Since we want perfect squares, meaning that the power must be divisible by 2. So we write all the powers that are divisible by the 2 that are less than or equal to the original power. Or in this case, 6, 10, 9 for 3, 5, 7 respectively. Considering that, we get the total for this one is 4. 4 possible values. This one has all of this. This is just total of 6 possible factors. And 7 to the 9 gets 78. 7 to the 9th doesn't count. 7 to the 6th, 7 to the 4th, 7 squared, and 7 to the 0. This gives you a grand total of 5 possible factors. Or 5 possible squares. Multiplying this all up gives you all your possible values. So the answer to this question is just 120 or C. Now let's move on to problem 19. How many further cube factors does 2 to the 4th times 2 to the 6th times 5 to the 10th have? Well, this is a bit of a different question now. Why? Because this is just now cubes, which means we want the power to be a multiple of 3. That's the key part. We want these powers to be multiple of 3. Doing the same method, we get 2 to the 0 and 2 cubed are the number of cube factors that are dividing 2 to the 4th, but not exceeding it. That's 2 ways. Similarly, 3 to the 6, 3 to the 3rd, and 3 to the 0, 3 ways. 5 to the 10th has 4 ways. Adds 4 ways. Multiplying this all up gives you B, or a grand total of 24. Alright, now let's move on to problem 20. A rectangular quilt has 42 squares. How many shapes are there in which the quilt can be arranged? Well, how do we approach this? Well, notice that this is basically, we do not care about composite figures, anything like that. We want to make it a rectangular quilt, or integer silent. Pop it out, just looking at the pairs of factors. So one way to do this is 1 times 42. 1x 42. Another way is 2 times 21, 3 times 14, and lastly 6 times 7. Alright? These are all the possible ways. And from there, you got 4 possible ways, so the answer is E, because that's the number of ways we can make shapes that which the quilt can be arranged in. Alright? Now let's move on to problem 21. What is the smallest positive integer by which 80 can be multiplied so the product will be a perfect cube? Factoring this will give you 2 to the 4th times 5. And since we want a perfect cube, we want the power, this is 1, if it's by itself, the powers must be multiples of 3. So how do we get 4 to become a multiple of 3 and 1 to be a multiple of 3? If we multiply the 2 to the 4th by 2 squared and 5 to the 1 by 5 squared, we can make this into 5 cubed and 2 to the 6th. This is the perfect cube. So all we have to multiply is 2 squared times 5 squared, which is just 100. So the answer to this question is just 100. Alright. Now let's move on to problem 22. For how many positive integers n will 60 divided by n also be an integer? Alright, so how do we approach this? Well, if we want it to be an integer, n is positive, this is just telling you that we're just looking at the factors. Since all the factors of 60 will always divide into 60. Alright? So let's try it out. What are the factors in 60? Or how many factors are in 60? Well, we can factor this into 2 squared times 3 times 5. Alright? Using the formula as we talked about previous classes, 2 plus 1 times 1 plus 1 times 1 plus 1 also, this gives you a grand total of 12, or B. Since all the numbers in this factorization, when you can pair it up in which ways you want, so these all will divide 60, since they're factors of 60, which means that all the positive integers of n must be also factors of 60. Right? Now, problem 23 is a bit of much a harder question. How many positive integer values of x are there such that 36 divided by x plus 3 is an integer? Now, we want this to be a positive integers values of x, so this is important. Same approach, let us consider x plus 3 to be y. Or maybe let's just consider x plus 3 to be a number by itself. Right? We want x plus 3 to be a factors of 36. Alright, so let's write down the factors of 36. 1, 2, 3, 4, 6, 9, 12, 18, and 36. Now, we have to subtract 3 because we want to know what x is, not what x plus 3 is. So if we subtract 3 on each one, and we want x to be positive also, so we gotta watch out. Notice that from 1 to 3, these will not be positive, right? Because if we do 1 minus 3, that would be negative 2. X is not positive. 2 minus 3, negative 1. X is not positive. 3 minus 3, or 0. X is not positive. And finally, we got 4 minus 3, which is 1, which is indeed positive. So we got 3 values and the factors of 36 that do not work. And we know there's a total of 9 values. So this becomes 9 minus 3, or equal to 6 possible ways. Just make sure you understand the restriction, since we want this to be positive. This clearly says to be positive. But this is not positive. These numbers are not positive. So the answer to this question is just C. Alright? In the equation, x to y is equal to 8,192, x and y are positive integers. What is the greatest possible value of x minus y? Now, one way you guys would have done this is to find which powers give 8,192. But there is no need for that. Since we want only the greatest possible value of x minus y, we could just let 8,192 be the base and raise it to the first power. That gives you 8,192. And this is the greatest possible base for x, alright? This really matters a lot, since we got the greatest possible value of x and least possible value for y. So from here, we know this is the maximum. So we do our subtraction. This becomes 8,191, or D. Alright? Example 21. How many even positive integral factors does n have if n is equal to 6 squared times 15? Notice that this is not the complete factorization. Why is that? Because 6 squared is just 2 squared times 3 squared. 6 squared is equal to 2 times 3, all that squared. Or 2 squared times 3 squared. 15 is equal to 3 times 5. We have to combine all these. These are the true factorizations. We combine these factorizations together. We should get 2 squared times 3 times 5. Alright? So from here, what's to the left is basically 2 squared times 3 squared times 5. 2 squared times 3 cubed times 5. So we got 3 copies of 3. So from here, the answer to this question is just 2 plus 1 times 3 plus 1 times 1 plus 1, or 24, or A. Alright? Now let's move on to example 22. Are you guys enjoying this question? And tell me your answer to chat. Alright, let's get started with this question. So, from here, notice that 2 cubed times 3 squared times 5, all positive factors is in half. Well, notice that we will only care about this. Becomes 3 squared, which has a total of 3 possible ways to happen. 3 to the first, 3 to the 0, and 3 squared. Alright? Times 5, this just becomes 3 times 2, or 6 possible ways. So there are 6 factors. Alright? Now let's move on to example 23. How many perfect cube factors does 2 to the 4 times 3 to the 6 times 5 to the 10th have? We already went over this before, so we can skip this. How many natural numbers will n will make 36 divided by n plus 1 a natural number? Well, this is pretty simple. Why? Because this is just basically the same question, but we only care about natural numbers. Alright? So, we know this that 36, as we factored before, there's 9 possible factors. Note that 1 is a factor. If we let n plus 1 equals 1, we get n equals 0. Does this count as a natural number, though? According to people's definitions, it should count as a natural number, but some people also say it doesn't count, only positive and number numbers. So, in this case, let's just say it doesn't count, alright? To make it a little bit harder. So that's just 9 minus 1, or 8. So the answer to this question is just 8. Alright? This question we also have done before. Let's move on to problem 26. How many positive integers from 1 to 100 have an odd number of factors? We did this in the last class, and we know that 100 is 10 squared. And 1 is equal to 1 squared. So there's a total of 10 squares between 1 and 100. So 10 squared is the biggest square, and 1 squared is the least square. Alright, so the answer to this question is just 8 or 10. Problem 27. What is the smallest positive integer by which 252 can be multiplied? So the result will be a perfect cube. Well, notice that 252 is divisible by 2 squared, also divisible by 3 squared, and divisible by 7. Alright, this is the factorization. From here, notice that 2 squared to get to a cube is just 2 cubed. That's when we have to multiply by 2. 3 squared, exact same thing, we gotta multiply by 3. And for 7, we gotta multiply by 2 sevens, or 7 squared. So we gotta multiply by this number in order to make it a perfect cube. Which, when we multiply it up together, is just 294. So the answer to this question is just C. Alright? Now let's move on to problem 28. How many factors does 21,600 are perfect squares? Same exact problem. We want to find how many are perfect squares. Well, notice that 221,600 is just 216 times 100. Right? Let's break it down. Now, this is just 6 cubed times 10 squared. We know 6 is 2 times 3 and 10 is 2 times 5. So this just simplifies to 2 squared times 5 squared times 2 cubed times 3 cubed. Combining like terms, 2 cubed and 2 squared, we get 2 to the 5th times 3 cubed times 5 squared. Now we're not done yet. We want to find the perfect factors of perfect squares. So we want to find the powers that are even. Alright? Well, 2 to the 4th, this is pretty simple. 2 to the 5th, it's pretty simple. It's just 2 to the 4th, 2 squared, and 2 to the 0. 3 cubed is just 3 to the squared, 3 to the 0. 5 squared is just 5 squared and 5 to the 0. So there's 3 ways for this way, 2 ways, and 2 ways. Multiplying this all together gives you 12 possible factors that are perfect squares, or E as our answer. Alright? That's it for today's class. Hope you guys have a wonderful weekend, and I'll see you next week. Bye!